Welcome to experiment number 7, and this is a lab where we're going to be studying the DC characteristics of a bipolar junction transistor. Now in this case, the transistor we're going to be studying is the 2N2222. It's a very nice general purpose transistor. It gives you good amplification, it's easy to handle, it's rugged, they don't very often burn out. You have to really try to burn one of these out. Unlike MOSFETs, MOSFETs kind of drop like flies because the gate is so delicate. So they come in two possible packages. One is the plastic package that looks like this. I believe that's a TO92 package. And they also sometimes come in a shiny metal package like this. And I don't remember the name of that package. But both of them are electrically identical. They're just in a different kind of package. If you get it in the plastic package like this, if you hold the flat side towards you, the pins go emitter, base, collector. And if you get it in the metal package, you'll notice there's a little metal tab sticking off on one side. That's next to the emitter. And then it goes base, collector as you move away from it. And I don't feel like I'm going to have to tell you to memorize EBC because you're going to have it drilled into your head for the rest of the year. For the rest of 310, we're going to be using these, and for much of 311 as well. So you're going to have a lot of time with these 2222 transistors, and they hold up very nicely. They cost, what, a nickel each? They're not even that. And so they're very cheap and plentiful, and they work very nicely as long as you don't push too much current through them. So what we're going to be doing is measuring the DC characteristic of the transistor, and we're only taking 3 curves. IB of 10 microamps, IB of 20 microamps, and IB of 30 microamps. So in not like we had so many curves with JFETs and MOSFETs, we're just going to be doing those 3. So we have over here IC. You're used to seeing ID over here, IDS, but now we have IC. We have VCE down here. This used to be VDS, okay? And then IB, these used to be VGS. These curves were each a different value of VGS. So what we're going to be doing today is measuring this set of curves, from this deriving a beta, and then we're going to use the beta to design a biasing circuit to build this transistor for a good DC Q point. Our test circuit looks like this. We have a positive VCC supply voltage. We have an RC here, a 10K brown, black, orange, just like we had with JFETs and MOSFETs. We have a base resistor here now, RB, and that's there to limit the current into the base so we can make this voltage anything we like, and we're not going to try to overdrive this base to more than 0.7 of a volt. We have 2 ammeters now, one here to set the IB, and one here to measure IC. And then we have a voltmeter here to measure VCE. So what we're going to do is we're going to build this circuit, apply a positive supply voltage here, and then we're going to set VBB to give us 10 microamps of current, and just take a series of points. Then we're going to dial up a VBB for 20 microamps of current, take a series of points, 30 microamps of current, take a series of points, and then we're done with part 1. That's what we'll be doing in the first part. Okay, and that's it for part 1. Already, okay. So here we are, we're going to do part 1, and this is a DC only lab, so we only need our meters, our power supply, and the breadboard, and that's it. So the equipment we've got is, we have 2 this time, Keithley 2000 multimeters, number 368 and 383. We've also got an Agilent model E310 dual DC power supply, number 688. And we are using one of these Fluke 189 true RMS meter, number 458, for measuring VCE. So I'm going to diagram the setup a little bit this time. So what we have is like this. We have our dual DC supply here, so we'll do VBB on the left side, VCC on the right side, and let's designate this meter here for IC, and this meter here for IB. So IB on top, IC in the middle, and this is going to be VCE on our multimeter. So this is how we're going to be setting everything up. And then once we have that organization, I think it'll be easier for me to not turn the wrong knob. Okay, so let's turn on the equipment and let it warm up. And we're going to start with V1 at 0. And V2 is going to also start at 0. Just so when we plug this thing, it won't be live. The jumpers are correct. We have a positive voltage for V1 and a positive voltage V2. The negatives are both tied to ground. So we can start wiring our circuit. So let's start with the transistor. Here we have the transistor in the plastic package and with the flat face facing you. We have to spread these leads apart a little bit just to get them to line up nicely with the breadboard. And so for that, I have my pocket survival kit here. And this is a fresh new transistor. It's got to work. So I'm just spreading the leads apart a little bit over here so that they line up a little bit better with the holes. Okay, and we can work over there. Toward the top side is easier because that's where the binding posts are. Okay, so emitter. The emitter is going to be jumper directly to ground. So we need a jumper for that, which we'll put in just a second. Okay, and then the base, referring back to our diagram. All right, what a guy. Okay, ask and ye shall receive. All right, good. So here is a jumper going to ground. This one has a little bit of oxidation on it, but it should be okay. It's not passing a whole lot of current. So here's the emitter connecting to the ground bus, which is the upper bus. It's connected over there. All right. So now the base, on the base we have a 100K resistor, and I'm going to have that go off to the left side since the collector is going to be on the right side. So here's our 100K resistor going to the base. If it'll go in there, yes it will, okay. And then from the 100K resistor we're going to the ammeter, and from the ammeter going to this supply here. So let's put these on DC current so they don't dance around and give us a headache. And then we're going to come out of our board. The rest of this is going to be mostly banana plugs. So we're going to come out of our ground and go to ground over here. Okay. Let's just tuck that under there. Okay. And then we're going to be coming out of the plus side here through this ammeter, IB, the top ammeter, IB. And then from the top ammeter, we're going to go to there. And then we're going to need alligator clips also, like 2 of them. Okay, so then we're going to go from the VBB going into the top meter, which is IB. And the ammeter, the input is always the white terminal. And let's tuck that in back there to keep it out of our way. And then we're going to come out of our ammeter to the 100K resistor. So for that we need another red lead coming out of there and going into this resistor here. On the collector side, we're going to have this one going into this meter. Let's again tuck this back here just to keep it out of our way. We're going to now have a red lead coming out of our VCC going into this ammeter. All right, thank you, sir. Coming out of this ammeter. Okay, so let's connect up our alligator clip to supply the base current. Going to our 100K resistor. And now on the collector side, we're coming out of here, going into this bottom ammeter. We're coming out of that ammeter. And for that one, we may as well just use the binding post. And then from the binding post, we go through a 10K resistor to the collector. So we need our brown, black, orange resistor right here. And to the collector is the pin on the right. From there, And then all that's left now is to connect up our VCE voltmeter. So we're going to, on that one, connect the ground, and I'd rather put the ground over here to the instruments than to the, I guess the circuit board here is going to be okay, although it's more out of the way to put it there. So we're going to ground the voltmeter there, and then the positive end of the voltmeter is going to go on the collector itself. Okay, so we need one more alligator clip, and then the collector is over here on the 10K. Now, so we don't have to have this thing horning in on the transistor itself. Let's use a jumper to connect the voltmeter to the collector. That way we can have the wire off to the side. So I'm going to plug in a wire over here on the collector terminal, and now plug in the voltmeter over here, and now it's a lot less obtrusive, it's a lot less in the way. So our circuit at this point should be built. We have our DC ammeter for the base is the one on top. We have our IC here, VBB, VCC. So at this point we can turn it on and let's let everything go. So we're going to put our meter on DC volts. And what we're going to start by doing is cranking up V1 until IB reads 10 microamps. It's going to read 0.01 milliamps up here. Okay, so we're going to crank up V1 until that reads 0.01. Okay, so that's 10 microamps of current going into the base. All right. Now we have nothing on the collector, which is good because the collector supply is turned off. And we have nothing on VCE, again, because there's no current flowing. Everything is dead. Okay, so we have our transistor, we have our circuit built, we're ready to start. And we're going to go use V2 to go to 0 and 0. So at 0 volts, we got 0 milliamps. Now we're going to bring V2 up until we see 1 volt here. 0.167 milliamps. 2 volts, and we're stopping at 12 volts. 2 volts, 0.18 milliamps. At 3 volts, 0.196 milliamps. At 4 volts, 0.233 milliamps. At 5 volts, 0.406 milliamps. It's not a bad idea to check that we still have an IB of 10 microamps, which we still do. Every once in a while, we should go back and check this. And at 6 volts, I don't think we're going to make it to 6 volts. So we may have to stop at 5 because we're up to 20 volts on VCC and we're only at about 5.4 volts on VCE. So let's just stop here. If you want to take one more point, we are at 1.6 milliamps at 5.4 volts VCE, if you want to just do one endpoint on that curve. And we're still at 10 microamps on the base, 9.8. So let's bring this down, and we're going to do a 20 microamp curve. So now we're going to turn up V1 until this reads 20 microamps. Okay, and we'll do the same thing again. 0 volts, 0 volts, 0 current. So now we're going to go to 1 volt here. .357 milliamps. At 2 volts, 0.385 milliamps. 3 volts, 0.417 milliamps. 4 volts, 0.503 milliamps. 5 volts. .989 milliamps at 5 volts. And at 6 volts, methinks we're going to run out of space. So we're up to 22 volts VCC, but we're at, if you just need one more point, 5.2 volts at 1.86 milliamps. So that completes our 20 microamp curve. So let's dial that down again, and we're still staying at 20 microamps here. Oh, get that out of the way. Okay, here we can route that underneath. Okay, and now, we've been staying at 20 microamps, so let's bring this down, and let's do our 30 microamp curve here. So we're going to crank up V1 until we get 30 microamps there. Okay, so again, we've got 0 VCE, 0 IC. Let's bring this up to 1. One volt, 0.568 milliamps. 2 volts, 0.611 milliamps. 3 volts, 0.664 milliamps. 4 volts, 0.804 milliamps. And we're just barely going to make it to 5 volts. 5 volts, 1.782 milliamps. So right now we're 22 volt VCC, and I don't really want to go any higher than that. So with those points, we should be able to put together a family of curves of the DC characteristic of this transistor. So let's turn this back down, and we can go ahead and do part 2.